And I'm not a teacher who likes to stand in front of the class and be like, properties of ionic compounds, high melting point. Like, you guys can read. So let me give you the clip notes. For the last little while, we've been working on the analogy of how like chemistry is like reading. Your letters, periodic table. Words, putting letters together. So if I say NaCl, you know it's sodium chloride. Well, one of the things that if you're learning to read, like say my daughter is kind of learning to recognize letters and eventually getting to words, if I put together the letters C-A-T, it helps if you know that that spells cat. Make sense? However, if you don't know what a cat is, it's still not helpful. Does that make sense? And so maybe you know stuff about a cat, like a cat has 4 legs and it's fluffy and it makes me sneeze. Okay? Well, that's kind of what we want to talk about today. Just because you know that something is called sodium chloride is not enough. I need you to know some of its properties. What are some of the things that we can attribute to it? And so here are some properties of ionic things. And like I said, you guys can read. I'm not a big believer in taking time in me reading this for you. But for the most part, ionic compounds can be defined as very strong. Ionic things are fairly strong. Usually they have high melting points. And although you might be able to break them in half, the 2 halves will stay like intact. They have a lot of strength in those compounds. Okay. However, if you put them in water, they dissolve. Some of you guys saw me earlier today. I was mixing some solutions up in those beakers in the front. There's actually some solid stuff that I stirred into the water. You guys probably know the word dissolving. Like if you've had Kool-Aid crystals and you stirred them in, you can actually break ionic compounds, which are normally very strong if you add them to water. And because of that, another property is that they conduct. I don't really have a lot to add other than just know some of these properties. So know that they have a lot of strength to them, they have high boiling points, high melting points, that they retain their shape, know that they conduct, and know that they're soluble in water. It's not really up to that here. Molecular compounds, however, are for the most part the opposite, actually. Molecular compounds are actually fairly weak in terms of how they bond together. Because of that, these have almost always the opposite properties of ionic things. They actually have very low melting points. Maybe I should pause for a second here. Do you guys know what a melting point means or what it refers to? What's the melting point of water? Yeah, that's where water goes from a solid to a liquid. Does that make sense? What's the melting point of, like, say, copper? High or low?
High.
Really high, right? If you wanted to take a solid block of copper and melt it, you're going to need hundreds, maybe thousands of degrees Celsius to melt it, right? Water actually has a very low melting point comparatively. Low being 0 degrees Celsius. Water is normally in a melted form. Does that make sense? But solid stuff, like metals, normally is all not melted. Usually it takes a lot of energy to melt them. So because they have a low melting point, they actually have a fairly weak attraction. They do not tend to bond with other covalent compounds. So that actually means that it's a very weak attraction between each other. I guess, here's that word. They're very weak. Imagine water as a snowflake. You know how we can freeze water and turn it into, say, snow. That's not very strong at all. I can break a snowflake. I can break ice fairly easily. It's not actually that hard to chip into pieces. So ionic things are fairly strong. Covalent are fairly weak. Covalent things are also not typically something that conducts electricity. And we're actually going to do a test on this on our lab on Wednesday. We actually talk about properties of compounds. Long story short is that if you have ionic substances, they turn into anions and cations, the negatives and the positives. If you have negatives and positives, things can conduct. Okay? However, molecular things don't have positives and negatives. They usually just have negatives. And because of that, they don't actually conduct very well, or at all. So in terms of properties, ionic things, strong. They conduct. They retain their shapes a lot, because usually their shapes are solids. Covalent things don't conduct. Usually they're fairly weak in structure. They usually are gases or liquids, because they have low melting points. Does that make sense? Let me just give an example to talk about that. NaCl. Anybody know what its formula is? NaCl, what's the sodium chloride? There you go. You guys probably know sodium chloride as just basic salt, right? What state of matter do you usually find salt in? Usually you'd say that this guy is a solid. We usually put a little S in brackets to indicate solid. The reason why it's solid is it's got a lot of strength in its formula. Ionic things have positives and negatives. They attract each other. So therefore it has a fairly high melting point. If you try to melt salt, like if you just put salt in the microwave, it probably won't melt. It'll just get hot. It probably takes hundreds of degrees to actually make salt turn into a liquid. Or even crazy as this would be, turn it into a gas. Does that make sense? Here is a different compound. CO2. Carbon dioxide. What state of matter is carbon dioxide? That's a gas. This is a fairly weak compound then. Carbon dioxides and other carbon dioxides don't stick together to form solids the same way that ionic things do, because they don't have positives and negatives. So because of that, this thing usually has a fairly low melting point. So low that chances are carbon dioxide has already melted and is no longer a solid. Probably not even a liquid anymore. It's probably all the way into gas form because it has such a low melting point. This one here, molecular. This one, ionic. Does that make sense? Okay. Water itself is actually a pretty unique compound I want to talk about for a bit. And there's 5 main properties of water that I need you guys to know of that allow it to be such a useful thing, especially in our lab. But honestly, it's the reason why life actually on Earth is sustained, is because of some of water's unique properties. Water is known as what's called a polar molecule. We'll focus on polar molecules in later years of chemistry. So for right now, all I just need you guys to know is that it is polar, meaning that it has positive and negative portions to it. Okay? And what it does is it causes water to cling together. Have you guys ever heard of the term adhesion and cohesion? You guys ever heard those words before? What does it mean if something adheres to something else? Yeah, it sticks, but to something else. Like if I glue something to the wall, I'm adhering something to the wall. Water has the ability to stick to, like, say, a wall. For example, here's my water bottle. I know you guys probably can't see it from here, but there are water droplets stuck up on the sides right here. They are not falling down due to one of water's unique polar properties that makes it that water can actually cling to the sides of its container. You guys ever seen that before? Okay. That's known as adhesion, the ability for it to stick to something else. Water also has the ability of cohesion, which means that it can stick to itself. That's why water actually forms in droplets. Because like when you get a drop of water, like if I were to have a water drop just like clinging off the edge right here, what's really happening is all of those water particles inside that drop are all kind of sticking together. That's known as cohesion. Does that make sense? Because of that ability, here are 5 properties that water has that are very, very important, just in terms of how our world works. So again, you guys can read these. I'm not going to read off the slides, but it actually means that water's boiling points and melting points are actually a little bit higher than you'd expect. You know how I just told you that molecular things have fairly low melting points? Carbon dioxide is molecular. It's a gas. Carbon dioxide is molecular. It's a gas. I'm just going to write some of these out. CO2, it's usually a gas. CO, also usually a gas. CH4, that's methane, is almost always a gas. And yet there's a really weird one. Water is usually a liquid. Why does water stick together? It's actually because it has a little bit of a higher melting point than you'd expect. Because of that, second property, water can actually store a lot of energy before you raise the temperature of water. It takes a lot of energy to raise the temperature of water. For example, let's say it gets really hot out and you've got a swimming pool in your backyard. You probably can't get the water in your swimming pool to boil. Does that make sense? Even on the hottest day of the year. Because it takes a lot of energy to get water to raise even a couple of degrees Celsius. Based on this property, this is why we actually cook our food in water. Because if we can get water to boil, it means there must be a lot of energy in that water as water is boiling. And that energy can then get transferred to our food and cause our food to get cooked. Make sense? So it actually, as odd as it seems, water actually needs a lot of energy for it to actually raise in temperature, comparatively. Third property, you guys have maybe seen this before. Because of the polar forces between water molecules, water will actually sometimes have a little bit of like a, I said to my grade 11s this morning, it looks like a bit of like a contact lens where it has this shape to it. The shape is called the concave shape. You guys ever seen this where like water has the ability to kind of bend around the edges?
Or like the elastic thing over top?
Sure, that's actually surface tension, which is on my next slide. This one's the opposite. What's happening here is these water molecules right here are being drawn slightly up the edges due to that adhesion concept. So the water is actually only supposed to be this high, but due to its polarity, it can actually pull itself up the sides a little bit.
Why does it do that?
Because of adhesion, the ability for it to stick to the side wall, just like these droplets do right here.
There?
Does that make sense?
Yeah, but like, what did it do on that?
On here,
Yeah.
you'll probably see a little bit of a meniscus here if it settles. Just find any water bottle, you'll see like a little bit of a curved surface at the bottom. Let me skip ahead to number 5 here. Gabe just mentioned the idea about how it kind of bends over the top. That's actually known as surface tension. Sometimes what we can have is like a cup of water, and this would be full, and somehow the water is just barely over the top. You ever seen this before where it's like over full? Yeah, that's known as its surface tension. That's because of water's ability to stick to itself. And so sometimes water can actually be a little bit more full than you think it should be. That's known as its surface tension.
Can like milk and stuff do that too?
Maybe to a less degree, but that's probably because milk has water in it.
Yeah.
Because like milk is not a substance on its own, it's a mixture. Right, and then last property, ice actually floats in liquid water. You've probably seen this before. That's actually very odd. Normally solid stuff will fall compared to liquid stuff based on density. Like if I had a rock and water, the rock would sink because rocks are more dense than water. But ice is actually less dense than water. That's actually an unusual property. So I'd like for you guys to know these 5 unusual properties of water. Okay, last thing then. One of the things we can do with all of this information is then figure out what state of matter we expect compounds to be. At least we can make a really educated guess. So here's some basic rules. If it's ionic, it probably is going to be able to dissolve. It might not, but it might. If something is dissolvable, we write the little letters AQ afterwards, meaning aqueous. You guys ever heard like aqua? Aqua is like a Latin for water, some sort of root in that word. Is that right? Yeah, language stuff. Okay. So aqueous means that it can dissolve in water. Okay. If a substance, though, does not dissolve well, it's only considered to be slightly soluble. And I want to show an example. Earlier today, I made 2 different solutions. They look like they're just regular old-fashioned water, but I promise you it's not. Because I took some solid crystals and I put them in here, and I put some crystals in here, and I stirred them all up. Would you guys agree that they dissolved? Okay. Many solutions do dissolve. However, sometimes when you combine them together, they don't dissolve.
Oh, I totally missed that. Crap.
What you watching?
Can you do it again?
How?
Oh, I don't know. I missed that. I looked away for 1 second.
How?
What did you put in there?
I just mixed the 2 of them together. They were both clear.
After this last door, can you show me? I'm mad at myself. I looked away for a second.
For a second. Okay. If you're not Gabe and you were watching beforehand, I had 2 clear solutions when I started, correct? I would say that those solutions were aqueous, meaning that stuff dissolved. However, when I poured them together, that is no longer aqueous. There's like a sludgy type of material inside of there that is considered to be no longer soluble. And I'm going to let this sit for a little while, and what you'll actually see is that a lot of like silty dirt type stuff is eventually going to settle on the bottom. Kind of like if you're at the beach and like you have like the sand at the bottom and the water, and then like you step in it and you ever get like the sand kind of get kicked up a little bit. and eventually the sand will resettle down to the bottom of the water again. That's hopefully what should happen here over time. This is no longer considered soluble. And so different compounds have different solubilities. What I need for you guys to be able to figure out then is, should it be a solid, liquid, gas, or possibly could it be aqueous? So here's how we're going to figure that out. There is a chart that typically gets given to students, and I actually have this in your, it's on your formula sheet. You guys know how you have the big periodic table? There should be one of these on the back of the formula sheet. Yeah, you got one right there. Nice to have yours. So I blew it up real big. It's called the solubility chart. So this chart will help you figure out, if you know how to use this chart, whether or not solutions actually do dissolve very nicely, or whether they're only, we call this slightly soluble, this one that's right here, where there's like a murky sort of sandy, I don't know, there's a bunch of crap in there basically. That makes sense? So here's how this table works. In order to figure out whether something is very soluble, which means it's aqueous, you need to look for something along the top. Usually these guys along the top are anions. And then you want to try to figure out whether the cation is either in the top row or the bottom row. If it's in the top row, it's probably aqueous. If it's in the bottom row, we usually write solid, because there is definitely a solid somewhere inside that container there. I might even filter it out later today to show it to you, but I'm going to let it settle first. I think the best way to do this is a bunch of examples. So my question here is, will these things dissolve in water or not? So let's start with KCl. If we have KCl, let's write it up top here. On this chart here, we need to try to find the anion along the top. The anion is chlorine. So can you guys find chlorine right here? That makes sense so far? Find a column with chlorine in it. Chlorine is very soluble with almost everything, except for 5 exceptions: silver, lead, mercury, copper, thallium. Is KCl one of those ones down here in the bottom? No. So that means KCl must be up here in the most category. So based on that, it is in the very soluble. I would expect KCl to be aqueous. If I added it to water, I would expect it to dissolve.
Was that thing AS on very
That's
soluble?
AQ?
What is it, AS or
AQ. Sorry, that's my really bad Q. My writing tool doesn't go that thin.
what does the AQ stand for?
Aqueous means it does dissolve. So before I poured those together, they were both clear. They both dissolved. This one right here, not dissolving. Clearly there's something in there. Kind of. Okay, let's try another one. CaCO3. So, I just, oops, that one was aqueous. Okay, so if we're looking for whether CaCO3 will dissolve or not, whether it's aqueous or solid, we need to find CO3, which is in this column right here. Does that make sense? Then we have to figure out where the calcium lies. Is calcium in the most? You guys have to have a column somewhere on there where there's a CO3, right?
It's in the middle. It's not really
Okay, this is a different table, but we should have you should still have a CO3 in a column somewhere, right? The bottom says most. Is that what yours says? The bottom says most?
Yeah.
And then the top says only with a group 1 or NH4? So I got a question. Is calcium in group 1?
Yeah.
Where's calcium? Calcium's in group 2. Calcium is right here. So based on that, it appears that calcium should be in this group right here, which means it's solid. So I would expect CaCO3, if it was in water, to actually remain in a solid form. Let me try a couple more and then I'll have you guys try some. MgF2. So look for a column that has fluorine in it. My table actually doesn't have fluorine on this one. Do you guys have fluorine as a column though? You do, okay. Is Mg in the top part or the bottom part? Okay, so if it was in the bottom part, then MgF2 would be solid. Let me try one more. Gold and sulfate. Here's my sulfate column right here. Gold is not one of the bottom ones. At least not on my table. Probably the same as yours. Okay, so then if gold is in the most column, the top row means it must be aqueous. So one more time here. If something is aqueous, it means it should be fairly clear. You should be able to see through it. It should be dissolved. This solution right here, you guys can come up and take a look if you'd like. Although it's yellow, you can probably see there's some solid stuff that's on the bottom of this container here. It is not dissolving anymore. There's a bunch of crud in the bottom down there. This is considered to be slightly soluble or solid, but beforehand it was actually aqueous, which means you could actually see right through it. So that's actually my lesson. I want to end it here because that's actually all I really need to talk about. A bunch of properties of ionic and covalent compounds, some properties of water, and a chart that will tell you whether something will dissolve and become aqueous or will not dissolve and look like that and be called solid. Does that make sense? Okay. Take a 5-minute break. When you guys come back, you have about an hour. So here's some recommendations. You guys can probably work on your assignment. I always recommend work on that like slowly but surely over the course of the unit. You could work on looking over your old tests, like your quiz from a week and a half ago. You could relook over your notes. I think I have some textbook questions and pages. Like here's some textbook questions and some things you can read if you like. To be honest, what you guys do at the hour is up to you. If you want to, you can even work on your research paper. But do something to help you learn. Sound good? All right, take a 5-minute break. When you come back, work on something.
I'm kind of confused about how